All right, guys, so let's start up here, find in your notes where we talked about ripple marks. And if you recall, I passed the ripple mark sample around the room, or one of you guys walked it around in each class. So you guys got to actually feel what ripple marks were and how they worked. Right, remember that you have that wave action or the water current that'll actually create these little ripples or ridges in the sediment. Then we also talked about angular and rounded sediments. And with the angular sediments, if we have rock that falls in place, like it breaks out of a mountainous area and just gets deposited very quickly, it doesn't have time to roll around and be abraded and round over those rough edges. Whereas when we have wind and we have water that are transporting that grain, it chips off at the edges and slowly makes a spherical shape. Right? So that chipping, that rolling, that bouncing, all of that's mechanical weathering that rounds over the grains. So when we look at a particular type of rock, like a conglomerate, that's going to have rounded grains that are all cemented together. Right? These are features that we're looking at in sedimentary rocks. Right, then we also said in sedimentary rocks that is the one rock type out of the three that are going to have fossils. Think about an animal dying and basically falls over and gets buried very quickly. Then the components that make up the bones will be replaced by minerals like quartz and aragonite. So that was that permineralization that we were talking about the other day. And permineralization is basically described down here in the notes, right? So organisms can be replaced by minerals and turned into rock. Petrified wood is the other example I like to look at, where the wood, the cellulose that makes up wood fiber, gets replaced by quartz and aragonite. Now, if I'm going too fast, you guys have the ability to just hit pause. You can come back and fill in whatever notes you need as you're going. But I'm just going to kind of roll through this so that you have the whole lesson. Okay, so the most common sedimentary rocks are clastic sedimentary rocks. And when we're thinking clastic sedimentary rocks, there are certain ones that you have to know. And that would be sandstone, conglomerate, shale, limestone. Now, I do want to make one note that limestone is going to fall into a couple different categories because you can form limestone a couple different ways. But just to get these names out there, sandstone, sand, glued together, sandstone, right? Glued, lithified, cemented together, right? Conglomerate is pebbles bound together. Shale is where we're going to have silt and clay that gets bound together. Right, so that's big picture. We'll get into a little more detail as we go. The next idea here is clastic. And clastic or clasts are fragments of rock. So when I'm talking about sand, silt, clay, I'm talking about different size particles or different clasts. So let's jot those down. And there you have, from left to right, from smallest to largest, clay, silt, sand, pebble. And I'll go into a little more detail on that tomorrow. Now here you see that we talk about clastic sedimentary rocks and we start seeing names like conglomerate and breccia. So here you see the word gravel, pebble, they're kind of interchangeable. And you're going to have rounded grains for the conglomerate. You're going to have angular grains for the breccia. Again, I'll show you guys samples of both of those. If you're curious right now, hit pause and Google conglomerate versus breccia. Pretty simple. When we look at the sedimentary rock with the medium-sized fragments, this is where we're getting into the sand size. That's going to make up sandstone. So again, we wrote those words before, but let's remember sandstone and the medium-grained fragments. Sandstone, we also saw in one class that it's porous. So in one of the classes, I actually poured water and we were able to see that it started to seep. I didn't get to that point in every class. My apologies. And just to recap, porosity is the amount of open pore space between the grains in a particular material. We'll use the word later, permeability, which is the ability for water to pass from pore space to pore space. So when we say that something is permeable, water can pass through it easily. A sponge, a towel, those are porous and water will pass through. When we say impermeable, that means that water cannot pass through it, and I always think raincoat or my glass windshield, right? Water's not coming through there, because if it did, my raincoat's no good. And if my windshield's permeable, then the whole car is going to get soaked, and that's just not going to be a good thing. I hope those analogies help you guys. And then finally we get down to the fine silt and clay size. And if I were a teacher right now, I'd be like, okay, which type of rock did we talk about? But for those that are like, can you just remind us, this is when we get into shale. And shale later on will get compressed and metamorphosed into slate and phyllite and eventually schist. We'll get to all that. But shale is basically your claystone, your siltstone wrapped into one category. So clastic sedimentary rocks are when we're gluing and compacting, right? Compaction, cementation, lithifying those grains together. That's only one category of sedimentary rocks. Then we have the chemical sedimentary rocks. And here you're seeing concentration of dissolved minerals in a body of water reaches saturation. Saturation means that the water has all that it can possibly hold. And it can't hold any more. And if you put even one more in there, it's going to fall out of solution, or it's going to precipitate. So this is pretty cool, because now we can make evaporites by driving the water off. You're going to keep hitting this saturation level, and with that you keep precipitating down. That's how, if you've heard of the salt flats out in the Midwest, that's where they go to like break the land speed records. The Midwest used to be under ocean. So as the ocean was getting lower and lower, the heat would cause a lot of evaporation, and you'd keep hitting this saturation level where the salt would keep depositing on the bottom, which is where you have Salt Lake City, you have the salt flats. All of this the result of evaporites. Now, if you're wondering where did the salt come from, it actually came from the mountains. Right? We dissolve sodium and we get chlorine there, it washes down into the ocean, and then from there it precipitates. I'm just going to recap before I move off this slide. Right here. Precipitate out of solution and settle to the bottom. Now remember, we talked the other day that sediments deposit in a horizontal manner. We made the analogy back to watching the snowfall. Right? Snow makes a nice horizontal blanket. Well, a similar thing happens when we're looking at precipitates, and that's where those salt flats that I was referencing, the reason they're so flat is because they were deposited on the ocean floor. And this picture, I think, helps you to see that just a little bit better. Right? The constant evaporation from a body of salt water results in precipitation of large amounts of salt. And here it's filling in. Now this is a curved bottom, and you're going to start to fill that in the Midwest, obviously a much larger, vaster area. All right, now one of the topics I really love to get into is how there's an interconnection of all of our science disciplines, right? Earth science isn't independent of biology or chemistry or physics. And this is a great example. Biochemical sedimentary rocks. Right? So this is where we're looking at the remains of living organisms, or some organisms that actually can contribute to the formation. And if you think of a coral reef, right, there are secretions that can actually build those corals. But one example there is limestone, composed primarily of calcite. So limestone will dissolve in, or can be dissolved by hydrochloric acid, HCl, And also carbonic acid can cause a dissolving, and we'll get into that when we talk later on about groundwater and karst topography. For right now, let's just remember that limestone is a great example for biochemical processes. You're having organisms that are contributing to the formation of limestone. Up in the front of the class, there's a gray rock up there. On the way out, you guys can look. There's actual coral. So it's a fossiliferous limestone. So I particularly like that one because it shows you both the reminder that sedimentary rocks are where you're going to find your fossils, and it's showing you the biochemical limestone. So this slide articulates what I was talking about with the formation of limestone and that biochemical process. We will see a clastic sedimentary rock called coquina, which is basically a whole bunch of shells that have been glued together. So that's going to be a separate category, but you're going to see a lot of overlapping here with the ideas that, hey, this organism made this shell, and now these shells are being buried and lithified, brought together. So we'll get into this a little bit more, but read through this slide in particular and really try to think about how these processes could all be working together. All right, now, I know I'm moving a little quick. I will recap on this stuff tomorrow. But for right now, you guys are going to at least have the notes filled in. I'll elaborate a little bit more. I really hope you're all taking the time. And if you see people that aren't taking these notes and going through them, you might want to give them the suggestion that I'm expecting that they've gone through and filled in their notes. Right? I'm not going to be spending time on Tuesday waiting for people to fill in things that they didn't do. All right, so that being said, we got our metamorphic rocks. And our focus question says, how can you tell when a rock has been transformed? The way you can tell that is take a granite. If we apply heat and pressure, the minerals will actually start to separate out by density, and you can get this thing called banding or foliation, right? Banding or layering, foliated, they go hand in hand. Secondly, sometimes I can see the original material, but I can see that it's been altered, right? There are metamorphic rocks out there where you can see the heat and pressure have taken grains and made them oblong in shape, right? You can see that there's been some force that's been applied. And in a case of a shale or sedimentary layers that have been compressed, you might still have that layering effect, but now it's been super tight and actually starts breaking off and making it what we call fissile, meaning that it'll crack off. And slate is a great example of that, right? If you have slate out in the garden, some people like to use them as paving stones and stuff like that. They actually chip apart into individual sheets. So we'll take a look at that on Tuesday. We'll get into that, when you guys have hand samples in front of you. But for right now, just take that idea that you can see the origins of the rock, but it's clearly been changed. So this slide right here is going to really lock in very quickly what metamorphic rocks are all about. We're saying high temperature and high pressure combined to change the texture, mineral composition, without melting. That's the big part. We're not going to melt these rocks, because if we melt them, if you recall, melting would lead to this thing called magma. And magma is how we make igneous rock, right? So we don't want that to happen. No melting. Instead, high temperature causes change, makes rocks ductile. Right, we can deform them. And think about the word metamorphose, right? You might recall back in the day you learned about a caterpillar that then makes a chrysalis and then metamorphoses, right? Goes through metamorphism and comes out as a butterfly. I mean, if you didn't have that experience in preschool, kindergarten, first grade, I apologize. Somebody has not done their due diligence to give you a basic understanding. If you need to see that, please let me know. I'll go buy you some caterpillars. All right, but that idea of change, metamorphism, right? It's going to take a little bit of time. And in the case of rocks, we're going to have some high temperature, high pressure to be able to make that change happen. So now you might be asking, well, where do you get the high temperature from, right? So high temperature required for metamorphism are ultimately derived from Earth's heat. So as we go deeper into the Earth, and we looked at that in the geothermal gradient, you guys answered questions in the first igneous homework about where you're going to be able to find temperatures of 800 to 1200 degrees Celsius. So it would make sense that we have to go back into the Earth to be able to find the higher temperatures. High pressure required for metamorphism comes from deep burial and compression, right? And this idea of mountain building. Now, we haven't gotten into mountain building yet. We will get into that a little bit more once we see plate tectonics. But just as a teaser, land masses are in constant motion on Earth's surface. You're just going to have to accept that as a statement right now. And there are times where continents have pushed into other continents, and that force of one landmass smishing into another one creates a lot of pressure, and that's where metamorphism can come in. The explanation I just gave you is the origins of most of New York State's rocks. I can take you into the Bronx and I can show you the Fordham Gneiss. Go into Manhattan, we can look at the Manhattan Schist, the Inwood Marble. All of these metamorphic rocks are because New York was an area of great mountain building and a tremendous amount of metamorphism as a result. So high temperature, high pressure, making these metamorphic rocks. Now, I said before, you take a granite, you can put it under intense heat and pressure, and you can actually start to form some new minerals. You can also alter the state of other ones. And now you actually have the definition for foliated. Right? Foliation meaning layering or banding of minerals. And my favorite example of that is a rock called gneiss. Now, gneiss is commonly used for those cobbles that people like to put along their driveway. So over in the cabinet, I actually have one of those cobbles from when we did my dad's driveway years ago. But in front of my house, I have a big old cobble, a big old boulder, actually. I'm not bringing it in because it's way too heavy to carry into class. I'll pull my back out. But it is beautifully banded, where there's a nice dark layer and then a light layer, dark layer, light layer, dark layer, light layer. And this is classic foliated banding gneiss. What really happened was granite was put under intense heat and pressure, and the amphibole separated in with the other mafic minerals, and then the felsic minerals like quartz and feldspar, they created a band, and it alternated back and forth. Now, this brings back the idea that we're describing rocks based on how they form, and if I don't make layers, then I'm not a foliated rock, and therefore this metamorphic rock, called a non-foliated metamorphic rock, is going to look more like, to me it looks like really large crystals, not pegmatitic, but like really, you can't really tell one crystal from the next, and I almost think it looks like slushy ice. So the two examples you have there are quartzite and marble. And I'll pass samples around of both. But quartzite, you don't see individual sand grains because you've taken intense heat and pressure And now all those individual sand grains have blended into one texture, and that's quartzite. Marble, you took limestone, you put it under intense heat and pressure, and so that calcite basically worked into one large marble, and you can't really, again, differentiate one crystal from the next. That's a key point there. When you look at an igneous, crystalline igneous rock, you can see the individual crystals. With quartzite and marble, you can't see the individual crystals. It looks just like somebody blended them all together, and it has like a slushy appearance. This obviously wouldn't be fun if I didn't give you another diagram to look at. So, let's look here. Increased grain size parallels changes in composition and development of foliation. Grain size is not a factor in non-foliated rock. So you look down here at the non-foliated rock, we have quartz making quartzite, we have calcite and dolomite making marble. Right? And this tends to be fine to coarse grain. The big thing here is that you have the pressure that blends those grains together. You look above there though, banded, right? This is where I'm talking about getting our granite, heat and pressure, boom, we can make gneiss. Above that, you have the layered rocks, and very clearly layered would be schist, phyllite, and slate. Now, those are actually different grades of metamorphism. Those are different grades of metamorphism. I can take a shale and make all three of them if I increase the temperature and pressure enough. So that's what this slide is trying to tell you. Different combinations of temperature and pressure result in different grades of metamorphism, and that's where we can have low grade, intermediate, and high grade metamorphism. Low, medium, high. But wait, there's more. Here we see low, intermediate, and high grade metamorphism on shale, causing different varieties of slate to occur. Okay, I'll talk a little bit more about that on Tuesday. It's a little easier when I can actually put the samples in front of you. Now, let's take a look at regional metamorphism versus contact metamorphism. Right? If you recall before, I said that New York State was actually formed by large-scale metamorphism, like the whole entire eastern seaboard, right? Maine all the way down to Georgia. Massive continent smashing into massive continent, making this massive Appalachian mountain range and tons of metamorphic rocks. That's what we mean by regional metamorphism, right? We can go from low to high grade. We can make lots of different metamorphic rocks, but it's over a very large area. Whereas contact metamorphism is going to be associated small scale. If I have lava that's flowing out in Uniondale, it might metamorphose the rocks immediately in Uniondale. But rocks that are sitting over in, say, Levittown or maybe into Suffolk County and Queens County, unaffected. It's the area that's in direct contact with that igneous body, in direct contact with that pressure and heat that are going to be changed. Remember, these are changes without melting the rock. If we melt it, then we're making igneous rock. The last type of metamorphism or scale of metamorphism is hydrothermal metamorphism. And here we're talking about basically chemical change due to contact with high temperature water. So if you've heard of Old Faithful, right, that's a geyser that keeps erupting superheated rock. But there's a lot of hydrothermal activity that's going down there. We also have hydrothermal vents in the bottom of the ocean, so lots of metamorphism that can occur down there. Right, so here it says near igneous intrusions and active volcanoes. So just to recap, Regional metamorphism, large scale, think Maine all the way down to Georgia. Contact metamorphism, only where you have an igneous body that is touching particular rocks. And then hydrothermal is kind of like contact metamorphism, but where we're using water to react with the different minerals. So with that, I've got 25 minutes on the clock. I'm going to stop the lesson there. And what I want you to do is start your homework, right? There are going to be questions. You guys have to do a little bit of reading. So use the time now to get started. And hopefully you don't have that much that you need to do tonight. Please remember you have a test on Thursday. So you want to be preparing for that. We're not labbing on Tuesday. Not labbing. So come full uniform to class and be ready for another lecture. Okay? I'll give you guys a practice test Tuesday night. We'll go over that. We'll finish up any notes we need to do on Tuesday. And then Wednesday we'll prep for the test. Thursday you'll have a test. So it should be good. All right? Have a great day, guys.